Okay, so we've done one example of using series to solve differential equations. We're going to do a second example now. Here's a new one that looks a lot like the first, but it's different. Y prime minus y is equal to e to the x. All right, let's solve that for the function. Let's think of a function who, when I subtract it from its derivative, I get e to the x. And you can think about it for a while on your own, but let's just go ahead and jump through it. Again, y has this series expansion, this Taylor series expansion, where again, these a naughts represent different things, a naught, a1, and so forth. And then again, I can find the derivative. So to find out the details of this, go back up in this worksheet or these notes to see it. But here again is y prime minus y. There's y prime. Those are like fours, those are y's. Equals, well, now it's equal to e to the x. So what's the series expansion of e to the x? Well, it's, again, 1 plus x plus a half x squared plus a 1 over 3 factorial x cubed, so forth. And again, like we did before, let's combine like terms. What's the constant here? A1. What's the constant here? A naught. What's the constant here? Just 1. So, well, first we're combining them. A naught minus A1 plus the linear terms, A2 minus A1, x. Here's the quadratic terms. Here's the cubic terms. That all equals 1 plus 1x plus 1 half x squared plus 1 over 3 factorial x cubed. So I've kind of grouped them where these things line up, and these line up, and these line up, and these line up, so forth. Those are the x cubed, those are x squareds, the x constants. So my constants are equal to each other. A1 minus A naught's 1. The linear terms are equal to each other. A2 minus A1 is 1. The cubic term or quadratic terms, this coefficient here must be equal to 1/2. Everything has a 2 in the denominator. That boils down to A3 minus A2 must be equal to 1. Likewise, for the cubic terms, everything has a 3 factorial in the denominator. So this coefficient must be 1 over 3 factorial, and that boils down to A4 minus A3 is equal to 1. So I can rearrange all of these to say A1 is just 1 more than A naught. A2 is 1 more than A1. A3 is 1 more than A2. A4 is 1 more than A3, and it keeps on going. You can see it. A sub n is equal to 1 more than A sub n minus 1. So again, we need an initial condition to settle out, like, what are the values of anything? So let's just start off with what happens if my initial condition is just 0. I picked this because it makes things the simplest. Well, that means that A naught is just 0. That's my initial condition. But that means then A1 is 1 more than that, and A2 is 1 more than that, and A3 is 1 more than that, A4 is 1 more than that. It keeps on going. That means that I have A naught is 0, plus A1 1x, plus A2 is 2, 2 over 2 x squared, 3 over 3 factorial x cubed, 4 over 4 factorial x to the fourth, and you can see where it's going, 5 over 5 factorial x to the fifth. Now I can do some simplification. 0 goes away. I have 1x. I have 1x squared. I have 3 divided by 3 factorial. Again, expand 3 factorial out. 3's cancel out. I have 1/2 x cubed. Again, expand 4 factorial out, and you have 1 over 3 factorial x to the fourth, so forth. And then I can look at that, and you might not see anything. But if you're clever, we could factor out an x and see that that is just x times 1 plus x plus half x squared plus 1 over 3 factorial x. Oh, this is just x times e to the x. So if y is equal to x times e to the x, is it true that y prime minus y is e to the x? Well, y prime, product rule, is e to the x plus x e to the x. So y prime minus y is e to the x plus x e to the x minus x e to the x. Yeah, that's this e to the x. It worked. Check my initial conditions. Is y of 0 really 0? I'll plug it in. Y of 0 is 0 times e to the 0. Yeah, that's 0. It worked. Let's try another initial condition. This one's a little bit trickier. What happens if I assume that f of 0 is 5? That means A naught is 5. And that means A1 is 1 more than that, 6. And A2 is 1 more than that, 7. A3 is 8, and so forth. And I have 5 plus 6x plus 7 halves x squared plus 8 over 3 factorial x cubed, 9 over 4 factorial x to the fourth, and so forth. Now this part takes a lot more cleverness than what I would expect you to look at from the first time through. And it helps to have done some differential equations, which I know you have done in the past, but it's also in the past, to know what to expect as an answer. What I'm going to do is I'm going to pull a 5 out of all these things. 5 is just 5, but 6 is 5 plus 1x. 7 here is 5 plus 2 over 2x squared. 5 plus 3, this 8 is 5 plus 3, this 9 is 5 plus 4. You can see the pattern coming here probably. And now I'm going to separate all these things. I have a 5, and then this becomes a 5x plus 1x. And then this becomes a 5 halves x squared plus a 2 halves x squared. And this becomes a 5 over 3 factorial x cubed and 3 over 3 factorial x cubed. This becomes a 5 over 4 factorial x to the fourth plus a 4 over 4 factorial x to the fourth. And now I can pull out the ones that have the 5s. I have a 5 plus 5x plus 5 halves x squared plus 5 over 3 factorial. That's all this stuff, plus everything else. I had an x, I had an x squared, I had simplify this. This is 1 over 2 x cubed. Simplify this. This is 1 over 3 factorial x to the fourth. Oh, this stuff right here, I just saw that. That's the same thing as x times e to the x. And this stuff right here, oh, I saw that in my first example. That's just 5 times e to the x. I have a solution of 5 e to the x plus x e to the x. Let's just check it. Is that really a solution? Is y prime minus y really e to the x? Well, y prime is 5 e to the x plus e to the x plus x e to the x. Again, product rule over here. So when I subtract y prime minus y, sure enough, I just get e to the x. And is the initial value truly 5? Well, y of 0 is 5 times e to the 0 plus 0 times something. That's just 5. So I can see that my general solution is probably some number a times e to the x plus this extra x e to the x factor on the end. Okay, so that's going to lead us to the homework, which I'll explain in yet a third video for this series.